Hello everyone, welcome to the channel Golden Barrel Technologies Private Limited. This channel is dedicated to helping students and professionals build a strong foundation and clear career path in VLSI and semiconductor industry. If you are confused about how to start VLSI or which path to choose, this video is specially made for you. Let us see about the today's lecture agenda. In this today lecture, we are going to discuss very detailed about digital ASIC or IC design flow. I am sure it won't be like a routine lecture. You will get very detailed and clear explanation about VLSI design flow. So watch it completely. I already told you this digital ASIC design flow we can also call RTL to GDS2 flow. Here you can whether it is a process or step happening in the VLSI design flow, everything I am showing like boxes for better understanding. Coming to the front end explanation. Initially, there is a specification or design ID. Specification we can know interface or port list, design architecture or algorithm or flowchart, or we can know the functionality, etc. These all comes under specification. Next, there will be a architectural design or behavioral description. Nothing but we plan micro architecture based on specification. Then, based on the specification and micro architecture, there will be a team like design team or RTL team. They will do design coding. Most of the industries using Verilog or System Verilog for design coding. Of course, there is VHDL also, but that is mostly used in FPGA. When we discuss about FPGA flow, that time we'll discuss about VHDL. Next, after design coding, it need to validate the design code functionality. So there will be other team, front-end functional verification or DV or verification team. They will write a test bench code to verify the design code functionality. This test bench mostly, most of the industries writing in UVM. Okay. So what is meant by design verification? Validating the design functionality with respect to the specification. Okay. So front-end functional verification is there, back-end functional verification also there. But what is important in front-end functional verification? In the back-end, whatever the functional verification happening, that is called, see here, post-silicon validation. This is after manufacturing or fabrication. If you detect any functional bug after manufacturing, there is no use, no? That's why this front-end functional verification is very important. That's why there is more demand to front-end functional verification. Okay. So here this front-end functional verification will happen like a mixed verification. It can be a scoreboard based and assertion based verification. Okay. So to verify the design functionality, there will be another approach like formal verification. This is also with respect to spec only, but it is mostly mathematics and statistics based. It is not like scoreboard based verification. So this RTL verification and formal verification both are like functional verifications only, but they are different ways of verification. Compared to this RTL verification, this formal verification is more accurate. And this formal verification can happen before synthesis and after synthesis also. Okay, right. Now what is meant by synthesis? There is HLS, high level synthesis. There is logic synthesis. But now this is about logic synthesis. What is meant by logic synthesis? Now here our code is in code format only. This is a verified design code. Now this verified design code will be converted into gate level netlist, that is called logic synthesis. Okay. Even after synthesis, we can do STA, static timing analysis. But mostly STA happen in the back end, and that is more important and more accurate. This we can treat like pre-layout STA, that we treat like post-layout STA. This is front-end STA. This is not compulsory, okay, but it can happen, okay. Then after synthesis, we can do gate level simulation, GLS. The GLS will happen, the simulation will happen on the gate level netlist. See here, already we did RTL verification. This is not on gate level netlist, this is on design code. And this GLS on gate level netlist. Okay. Then there is another concept, LEC, logic equivalence check. This is also like a formal verification that happen after synthesis. What is LEC? See here, this GLS verification result and RTL verification result, we compare whether logically both are equal or not. That is called logic equivalence check. Okay, now. Then after that, there will be DFT, design for testability. Why this DFT? What is this DFT? What is the necessity? For example, after manufacturing, you know, this VLSI chip may contain millions of transistors connected together. If there are any connectivity issues or defects after manufacturing, it is not possible to detect those manually. So we need some mechanism or technique after manufacturing to detect the defects, any connectivity issues in the IC. Okay. Manufacturing defects. Okay. Nothing but testing. Okay. So to do that, to get that facility, to enable that facility, we need to have some mechanism that is called DFT. So before fabrication only, we insert scanning, insertion we are doing. Na? We apply this DFT technique at this stage before manufacturing only. So that after manufacturing, you able to detect any manufacturing defects. That is called testing. So until this, you can treat like a front end. Even this DFT we are showing in the front end. Because of this, the testing or defects we are checking in the back end also. Okay, right. We discussed about back end part. For example, we can start with floor planning. What is meant by floor planning with respect to IC? For example, if we take our house construction, we do planning on soil, land, soil floor. But this planning of IC on silicon floor. However, we plan our house like hall should be here, kitchen should be here. Here also, there will be different subblocks in the IC. We have to plan which blocks we need to keep in which place. For example, if there are blocks that need to communicate frequently, then it's good to keep them nearby. And if there are blocks to communicate with external world, input outputs, those blocks we need to keep at the periphery of the silicon floor in the chip. Okay, that's kind of planning is called floor planning. Now placement. According to our plan, we need to place the blocks, that is called placement. Then clock tree synthesis. You know, different subblocks may need different clocks according to the requirement. But there is a clock source. From that clock source, we distribute the clock to different subblocks. It will form like a tree. That's why clock tree synthesis. Then we call routing. What is meant by routing? Suppose different subblocks in the IC need to communicate. There should be connectivity, nothing but routing between those blocks. Okay. Then coming to the post layout STA or layout verification, sign off. Suppose I told STA, static timing analysis, generally in the front end, we are concentrating mostly on the functionality only, not on timing simulation or verification, but here we take care of it. And this is compulsory and more accurate than all other timing verifications. Okay. Then what is meant by layout verification? For example, after doing placement and routing, that is nothing but layout. we need to verify its performance like timing, path delay, power, silicon area, all these things. If we get a satisfactory report, then we'll go to the next state, that is called sign off report. If we don't get satisfactory report, we need to go back again for the for planning, placement and routing until getting satisfactory sign off report. Okay. Then after that sign off, we need to send the GDS2 file to the foundry for the fabrication. That sending GDS2 to the foundry is nothing but tape out process. Okay. Then after fabrication, there will be post silicon validation. This post silicon validation also like a functional verification, but this is like a back-end functional verification. We already discussed about front-end functional verification here. But what is the difference? Which is most important? See here, this post-silicon validation or verification happening after manufacturing, after fabrication. If you detect any functional bug after manufacturing, what will you do? There is no use. Okay, but that's why this front-end functional verification is very important. That's why it has more demand. This is very important. Okay, but here, according to this post-silicon validation, we can know one more thing. Here, this design verification happening with respect to the specification. Here in this post-silicon validation, what we doing, whether this fabricated chip suitable to according to our real-time application or not, like that we check. Okay, that process happening here. Okay, right. Then you will get chip or IC. Then to detect any defects or connectivity issues, we need to test that. See, here we already incorporated some mechanism to detect the check the functional that to defects, connectivity issues. Okay, that we doing here. This is called testing part. So after finally testing, we will get a final product. That product can be any electronic gadget which contains some VLSI IC. Okay, right. This is about backend. Why we call it as a backend? It's happening at the end. Why we call it as front at the starting or front in the VLSI design flow or in the IC manufacturing flow. Okay. We can see another diagram from standard book. Initially, there is a design idea specification, then front end part or logic design part, coding part, then back end part, nothing but physical design part. Even it is ASIC flow. Here you can see FPGA flow also. This FPGA prototype information also we are using in the ASIC. Okay. And observe we started with the behavioral style in the coding part. Then coming to the another diagram, this is also from standard book. Here, what this back arrows showing. Suppose this arrow, when you did RTL coding, you may edit again and again. That we doing when you do any syntax errors. Okay. After functional verification, also back arrow. If you detect any functional bugs, you need to do RTL coding again. No? You need to modify. That's why. And here after logical verification also same. If you detect any bugs after logical verification, then also you need to go back if necessary. Okay. And here after layout, there can be two arrows. Suppose one is going to for plan and placement and routing. It means if the performance is not satisfactory, again you need to do for planning, placement and routing. Even though you do again and again, still if it is not satisfactory, you need to start again from design coding. That's why this arrow. Okay. Finally, coming to this slide, here you can see different short-term and long-term courses. Whatever the digital IC design flow I explained, in that there are so many things happening. To get that knowledge, you need to learn so many things. So here you can see in the front end, I have shown you RTL design. So RTL design and integration is one domain. You can take that full length course. Okay, placement oriented industry standard course. There is a DV design verification course. There is a DFT course. There is a PD course. These four courses are available with us, training and placement. And there are some short-term courses also related to that digital IC design flow. Okay. So there is some assertion-based verification or system Verilog assertion language. Okay, SVA. You can take that. Formal verification course. You can take that. Logic synthesis also. Gate level simulation. Logic equivalence check. And physical or layout verification. Okay. Then static timing analysis STA. Post silicon validation and testing. So as of now we have SVA, formal verification, logic synthesis, STA. So the cell EC, layout verification, post silicon validation and testing. In future we start. In the next lecture we'll discuss about analog IC or ASIC design flow and also about analog mixed signal design and also about AMS verification. So like it, share it and subscribe to Golden Barrel Technologies Private Limited channel.